Hello. Hey, good morning. I think I was in a bathroom or something. I could not because I had to take my dog out. Okay. Anyway, so I can give you my credit card number.
Hey, Rajesh,
Yeah, I have
Tony.
one question before that. When you had this soap dispenser changed, what was the previous one? Can you put it back?
Hello, can you hear me?
Yeah, but what
Hey,
was the name of the?
Tony, yes, I can hear you.
Yes.
Okay, thanks.
Well, I did not see it.
Yes, David.
Huh?
Hey everyone.
Michael, I want. Can you put it back in the drawing or just to for my understanding?
Hey Rajesh, we can hear you.
Yeah, so Blanco, if you have an
Hey, Rajesh, your mic is on. You can hear
okay, so
you.
but do you know anything specifically was ordered or specifically was selected like a black color or something? Oh, okay.
Okay,
Okay.
so well,
But that is all these soap dispenser are standard
a
holes.
second.
Yeah, maybe chat him and see.
Oh, understand. But the base square and all that stuff it is same, right? Okay, thank you. So let me give me 1 second. I am getting wait. Oh man, I can't believe this. Sorry.
Yeah, I just
Thank you.
Yeah, let's see. Okay, so today we are going to have presentation from Mark and his team. Do we have the right people on the call for that?
Mark who?
Mark Malinowski. There's
Oh,
only one Mark, D Mark.
The Mark. I don't
Yes.
see the Mark on the call.
I see Ahmed. Hi, Ahmed.
Yes, hi.
Are you from Mark's team?
Oh,
Yes.
Ahmed's gonna.
Okay.
Hey, Ahmed. How are you?
Hi, Tony. We are waiting for Petri. He's supposed to be here also to do the presentation, but
Okay.
just let me try to text him here. See, give me 1 second.
Right. Okay. Let me do this. Marcus, this. Okay. Uh, 7. Kevin. I saw Roger. I saw Ahmed. Let's see who else is here. Okay, is here. Oops. Okay, I think I captured everybody. Okay, now let's hope. Yes. Okay, let's give. Okay, while waiting for this, give me a second. Okay. Guys, one thing I realized, I didn't put proper titles, especially for the doctors on the call. So I know Jawad.
I'm okay not being a doctor.
I'm sorry,
I'm okay not being a doctor.
but you're okay with being a doctor too, right?
If you strongly feel, sure.
Yeah, I think that's fair to have the doctors named. My question for everybody else is, who else is? Do you guys know who else has a doctor title?
David, you can make me a patient.
You have always been a patient. What are you talking about? Do you know if Lal has a doctor title?
He does, yes.
Okay. Li Hong?
I think yes.
I believe so, yeah.
Okay. John?
John, no. I don't believe so.
No. Boone, how about you?
No.
Okay. KK, do we know if KK has title, doctor title?
Yes, KK is a doctor.
Okay.
He's a surgeon.
Are you sharing something, David?
I am. Are you seeing the white paper?
No. I'm on the web version.
Okay. How about everybody else?
I can see the screen.
Yes, we can see it.
You may want to.
I can see the screen too.
Okay.
You may want to restart, Tony. I think that.
Well, they reloaded my
Yeah.
whole computer, upgraded it, Windows 11, so I don't have the native, so I'm using the web version.
Yeah.
Seeing,
Tony, you have to go to a computer doctor.
I did. I was there all day. And then I had to go to a specialist this morning to fix what the doctor broke.
Okay.
Not having a good PT
You
month.
know what they do with, yeah, you know what they do with lame horses, right? Maybe the same thing needs to happen to your computer.
No, this is a new computer. We already shot the old one. And the new one was supposed to be pre-configured, but it wasn't.
Okay.
Let's move on.
I see Petri has joined us. Did I pronounce that your name correctly?
Petri.
Yes,
Pet-
I'm here. Sorry for being late. We have a terrible fog here.
Not a problem at all. Okay, just to finish this up, Roger, are you a doctor?
No,
Okay, Mark, do you guys know if Mark is a doctor?
I do not believe so. Ahmed is.
Okay,
Are you?
no,
how about Satish?
I don't believe so.
Okay, all right. Wanted to do this update. Then, okay, very good.
I'm still not seeing.
Now, okay, I'm working with on the topic of the white paper. Working with Bapi. The release flow has changed a little bit. It was somewhat simplified. The only complication right now that we have is that the server team is not going to meet this year anymore. So we are trying to get a shortcut to the server team, show the white paper to them, and then move on to the incubation, or was it IC incubation committee. Again, that has changed as well. We don't have to go into presentation, just one person from the incubation committee needs to go and sponsor that paper, go in front of the IC, show it to them, then they will review and give us their feedback, and then the whole thing gets published. So it's a lot simpler than it was before doing multiple presentations. That's the good news. I'm working with Bapi to get this thing to the server team. So that's my quick update on the white paper. Now, let's get back to business. We are looking forward to the presentation. Whoever is presenting, please go ahead and share. And the floor is yours. Is this going to be Petri or Ahmed? Which one of you is going to present?
Petri will present.
Petri. Okay, Petri. I apologize. I promise I'll get the name correct by the end of this meeting. Okay, go ahead, Petri.
It is. Yep. Let me just get my tools up here. So. Okay. The startup phase takes quite a while. Okay, let me.
Petri, you can start with the slides.
Yeah, I want to go directly to the real stuff. So the background of this this design is the US Post had some time ago a project in which they tried to create a letter sorting device that can also read the handwritten postal codes. And as a result of that project, the MNIST algorithm was implemented and it became to a kind of a hello world for machine learning. And because this algorithm is very flexible. It can be used for many different demonstrations and experiments. We have used that. We have the whole process starting from this capability analysis down to the RTL, and this is the whole flow that we want to show with this demo. So starting from the system analysis, first we need to well, let's get one step back. So we are using Arcadia methodology, and this is combined with a couple of other methodologies like PMM, and Arcadia itself doesn't have the functionality mapping, and this is something that we have been experimenting with a couple of universities here in Europe, and I think we have a solution that might be interesting. So we start from capabilities, and then based on the capability analysis, we build a first functional architecture. And the functional architecture, it has the system, it has the actors that are communicating with the system, and the functions that the system should provide. And we have also allocated requirements. These are coming from Teamcenter, and the requirements have also parameters that are also allocated here in this diagram. They are not necessarily shown everywhere, but they are there. So the next step here is that we start to analyze that how we should put these functions together. What is the logical architecture of the potential implementation of this device? And here we have found out that we have two potential software candidates, which are the digit recognition and the digit detection, the image detection algorithm, and the digit recognition, which is the MNIST algorithm. Then we have some other components here around, like power supply, serial interface, and the scanner head itself. And moving forward to the implementation model, so I have put these biggest algorithms to the SoC. And this I will analyze then further in a separate subsystem. And the whole gray box here, it indicates the overall device. And the yellow one here, this is the main PCB that contains the power management USB controller with all the components around and ASIC. So now I can transition this component to a new subsystem. And with the subsystem transitioning, I propagate all the requirements, all the parameters, functions, and exchanges that are inside this ASIC component. I propagate them to a new system, which has then different actors, because we are now no more talking with the user, the host computer, and the document. We have the scanner component, power management, and the USB controller. So this is the new subsystem. And now I switch the tool, because here I have also the analysis capabilities. And I have my starting point here, which is the same as we saw in the previous tool. And now the image detection is fairly simple algorithm, so it can be kept as one single function. But the digit recognition, is a neural network with multiple layers. So this must be broken down into the individual functions. So I do first my function breakdown, and at this point I already have decided that, well, max pooling and convolution, they belong together because they can be combined very easily. And parallel to this, the system creates a data flow diagram which has all these functions that I have added here are also here, and the exchanges between the functions. So at this point, we need some more information because here we have the image size and the image rate, but for the image recognition, we need some requirements that are propagated from the top level system. And these are the digits per second and accuracy in percent. And these are also included here, but additionally, I get from the algorithm guys the implementation properties. What is the kernel dimension? What is the feature map size? How many output channels must the convolution have? Max pooling, what is the pool size and stride? And on the dense layer, what is the feature map size, number of weights, and so on. So now I have my detailed model, functional model of the subsystem, and now I can move to the logical architecture in which I start to partition these to different logical components. And now this one of the beauties of the Arcadia methodology, that I can separate the functionality and the architecture. So I can move functions between the architectural elements and also create different kinds of exchanges between the elements. And in that way, I can try different architecture options. And to know what is the best one, we need to simulate it. So here we come to this PMM methodology. And at this case, we create a performance model in which we have ECU, which contains one or more SoCs. There is a CPU cluster, and the CPU cluster has one or more CPU cores. And then I add here software tasks that contain my functions. And these are allocated to the separate hardware blocks, and also the communication links between the functions that we can also analyze the data traffic. And the system generates automatically this performance simulation model. Here we add additionally the triggering functions that we have either timing event or data receive event. And let me change the view, then I have a little bit less stuff here. So we have also the communication channels with the data size that we are transporting between the functions. And now we can simulate this. We have possibility to create different simulations with different parameters. For example, simulation time, or we can use environment variables there and some common settings. And when I run this simulation, it is all running on the background. And then I get different results based on the parameterization of this model. And there are several different parameters that this model contains. One is the clock frequency and CPU architecture family of the processor cores. Another one is the load of each function. So we have two options here. We can use a synthetic workload, or we can use source code that we include into the model, and then we can analyze the real source code on this environment. I'm using the synthetic workload because it gives me the possibility to play around with the different implementation ideas.
So I'm sorry, what's the definition of a load here? You have a value against it? Is this,
So the load is principally it is one instruction, but based on the on the different processor architectures, one instruction may take multiple clock cycles. So this load value is principally one instruction, and this is a statistical average because also the different instructions may take different numbers of clock cycles on different architectures. So we start here with the instruction count.
oh, okay, so this is the instruction count.
Yes.
Oh, is it the count or the count times time?
It is instruction count.
Okay.
Because the count times time comes then with the simulation model.
Okay. And the instruction count per unit time then?
Instruction count per each function. And that's why I had to break this neural network to the sub-functions that I can give the instruction counts for each function. There are different ways to count the instruction count. For example, I'm using the value that we got from one simulation. I know that my convolution is doing about 400,000 multiply accumulates, and on this CPU type, this processor type, one multiply accumulate takes in average 37 instructions. So that's how I have calculated that. So while the simulation is running, I can show some results that I already stored from the previous simulations. And this is now the result when I've simulated that as a full software implementation with 3 processors, and I can see that the convolution task must be accelerated. It has no chance to get into the real implementation. And we are also storing a lot of different traces. So we have the function trace on each processor. Okay, now the new simulation results came up. And then we have for example, current function from the virtual platform. We have a task. Where is that? So we have the task execution profiles for each of the tasks on the different CPUs. We have communication profiles, so we can see what is happening in the queues. For example, the convolution outputs 20 data elements, so we can see that these data elements are here. Then we have CPU utilization profile. We have possibility to analyze each port individually. For example, these are the convolution process input and output ports. So we can see that there's a long processing delay between input and output. And we have also here the output from the convolution, which is all the 20 data samples. So when I go back to my system, now I saw that my convolution takes too much time, so I will simply change that to 15,600 instructions, which comes from the 392,000 multiply accumulate operations divided by 25. So if I create a hardware accelerator with parallel processing of the kernel, then I have 25 multiply accumulate operations parallel. So now when I run this simulation, I get another results, and here I can see that my CPU1, which is the convolution task, it has only 1% of the interval time, which is 1 second. So this all fits into the 10 milliseconds. And my target is to get the whole processing in 20 milliseconds. So I still have to speed up my dense layer. And again, I go back to my performance model, and I change my dense layer, which is 19,800. The number comes also from implementation option of the hardware accelerator. And now when I simulate this one, I get the result that both convolution and dense layer go into the 10 millisecond limit. Both softmax is now the biggest task. It is still running on the CPU 0. And now if I change my interval time to 20 milliseconds, and I keep this combination of the tasks, so I see that the CPU 0 is pretty heavily loaded, and the two accelerators are almost not loaded at all. And here I see also that my max pull function, which is now on the CPU 0, I could move it to the convolution accelerator, and then I get 25% of the CPU load away. So now getting back to the system model. So based on these results, I can then create a physical architecture, which is then my chip architecture principally. I get my CPU core and a software part. As a logical component, I get my convolution accelerator and dense accelerator. I have to add manually my interconnect and other non-functional parts, in this case, which are RAM, ROM, and UART. So these parts are important for the hardware implementation itself, but they do not contain any active functional processing. And from this model, we can then extract different types of outputs. We can move to the virtual platform. So we can extract this architecture and create a virtual platform skeleton. And here we can add properties like CPU type that we can then use to automatically allocate some components in the virtual platform. In the same way, we can also use that as a starting point for RTL implementation. We have the basic architecture here, and we know what is the CPU core we are using. We must go to the high-level synthesis process to create the two custom accelerators. It is another story. Takes again half an hour to explain it, and then AXI, RAM, ROM, UARTs are usually standard library RTL IP. So that's the process in a nutshell. Any questions?
So you mentioned that here the AXI is a standard RTL piece. So you can plug in RTL into this analysis ahead of time, or
no, no. It is just we are creating the RTL architecture here, but not the functional RTL itself.
Okay. You have the connectivity then between the different modules based on this diagram?
Yes.
And how detailed is that connectivity? Can you define that? Say, we're looking at this from a chiplet perspective. Let's say we wanted to build, this system out of chiplets. If you're doing 2.5D integration, they're going to get connected with standard interfaces like UCIe Express or BOW. Can we define those predefined buses to make those connections?
Yes, we can. And we are still in the research phase, but we have a couple of German universities who have been studying this interface mapping quite a long time. And we will probably be able to use IPExact, so that like we connected here at this point, we have performance properties and simulation properties, which have the file type and file name, and additional what we need for automated simulation creation would be interface description, because otherwise we cannot automatically create anything.
So would that be like a library based where you can define your own libraries, or is this hardwired?
IPExact is standard. It is machine readable file format that describes the interface of the RTL IP at the signal level. And in the same way, because this is a class-based architecture, we can create also more complicated data structures. And in that way, we can define that this is now our interface. And when we use this interface on the both sides, then the connectivity is guaranteed.
Right.
Tony, I think ideally for 3D IC, we're going to have a special library like the palette on the right that Petri showing there. We're going to have probably a section for
Ahmed, I would be careful with that, because if we use a library, then we have predefined interfaces. If we use IPExact, then we have full freedom to define any new interfaces or custom interfaces if needed.
Right. That's for advanced users, we can do that. But for people that they want to just experiment with things for 3D IC, then we can have a library for that.
Sure.
Yeah.
This would be then the library on the 3D IC design side, and we just add here property telling that we are now using this interface for this interconnect.
Okay, we do have standardized JEDEC models for all the interfaces that we would be interested in.
how many interfaces are standardized?
Probably, I'm guessing about 100 altogether. Most of those are what I call chip-to-chip. Those are interfaces that go outside and would be used typically for board level connections. So like DDR and Ethernet, PCI, those kind of interfaces. Inside, it's actually much fewer. Inside the package, it would predominantly be UCIe Express and BOW. So there's really just two, and we'd probably want a simple, just GPIO type.
So in that case, I think the library approach is is reasonable.
Okay.
But on the outside world, what we also can do, so principally, and in this level, the SoC could be the interposer, and the components here are chiplets.
Right.
And now the two accelerators, they can be custom chiplets. And CPU is standard, RAM, ROM, UART is standard. And how do we implement the AXI in that level? But probably 3D IC has a different bus structure.
Yeah, actually, I left one out. It would be HBM also. So your memories you could use HBM memories in the package.
Yeah. So principally, these exchanges between the physical components are the most critical ones, because these define the physical interconnect.
And do you consider test interfaces at all, like JTAG, IJTAG, SSN? Is it something that's even considered for this in this tool?
Yeah, this is a philosophical question, because we must reduce the data and on the system level as much as possible. And that's why I don't give here any detailed implementation stuff, but just the CPU type that we have here, Cortex A57. For the exchanges, I didn't define anything, because
could you just treat that as another library, like a test library? We're not really concerned with the functionality. I'm just really looking for the interfaces.
So principally, we can attach any property to any element here. So if we tell here that this interface is library type this and this, and when we extract the information from the database, we can then see that this particular interface uses data type this and this, or connection type this and this. So this property methodology gives us all the degrees of freedom to define whatever we want.
Okay.
So I've burned half an hour time. Should I release the screen and let?
No, you could. No, please continue if you have more. Actually, I have a quick question. So
yes.
The expectation then is that for these components, like say ARM or even AXI, that these will be pre-characterized in terms of performance. And
in this level, we principally don't need any characterization information. Where we need it is in this performance simulation level.
Yes. Yeah. Basically, somehow I understand. So for generating the system schematic, I'm not sure if that's the right word to use. What do you call this? Do you call it system diagram, system schematic?
These are architecture diagrams,
Okay.
And the Capella tool has lots of different types of diagrams. And principally, we have these data flow diagram, which is for the functional description of the system. And we have these architecture diagrams, what are the logical architecture and physical architecture. And physical
what are the three again? Architectural,
we have
physical, and what?
the data flow. Ahmed, do you remember the right name for it?
Yeah, so we have the system, which is you define the system. Then when we go to the logical level, here where we can define the software blocks versus the hardware blocks. And the physical is when you're going to do the implementation and the final, basically the physical architecture of your final SoC. Then what Petri showed you also, that is a function chain or function blocks that will show you how the function is collaborate or work with other function. And you can show all the activity across the function. There is a lot of things we don't need to go through here,
right.
but in general, what you need is really a logical diagram and a physical diagram. The logical diagram will represent the architecture for your hardware and software. What you expect, what's your load of software, and what's your hardware characterization.
This is the logical architecture.
Yeah. And then when you go to the physical, then Petri will define this. This is the CPU we're going to use. This is the clock rate. This is the information about your priorities for your signal, things like that. All the details that require to run that.
So those are primarily for architectures, and then anything else in your system would be kind of black box models that you would define.
Yes.
Right.
And
yeah, quick question. Do you have what is it, David? What's the processor we used in the demo? RISC-V. Sorry.
Yeah.
Do you support RISC-V?
RISC-V, I think it is being developed. I have here just a subsystem of subset of CPUs that we have available.
Mm-hmm.
So these all the CPUs, they are just libraries that we plug into the tool.
So ARM and Tricore is the last one.
Tricore, RISC-V is there, and Ahmed, do you know what are the Vista supported processor families?
Yeah, we pick these families as a starting point based on some automotive customers, but the team that building the library is always coming with a new family, so a very specific family. We need to think about it. Probably that's good time here to.
Yeah, but RISC-V is so common that
yeah,
it is there.
Yeah, we should do that. What about FPGAs? Do you support any FPGAs?
FPGA is not treated as a processor per se. It is treated as a generic hardware block.
Okay.
And there are also models for example, the Xilinx Zynq. But
okay. All right.
because here what we are doing is to analyze is that what can be run on the CPU and what should be accelerated with hardware.
Okay.
And that's why I'm principally misusing these CPU models here, that I just give here the load that represents my hardware accelerator processing speed.
Mm-hmm.
And in that way, I can estimate the performance. So here are all the possible diagrams that we have. So we can start with very abstract levels. Then we have the function breakdown. We have functional data flow that we saw, system architecture. Then we have also additional diagrams for interface definition. That's something we should look at before we start to create libraries. Because that could be also one possibility.
This is excellent, Petru. Thank you. We've got about 10 minutes left. David, would it be good to maybe do a 5-minute overview of our OCP demo and just so they have a feeling of what we're doing and you know we're trying to consider putting a system level model on top of that. So I think just if you could just pull up maybe just your couple the slide deck that we did at OCP, that'd probably be all we have time for.
Why are you doing that?
Slide deck.
Yeah, do you have that handy or?
No, I can pull up the actual tool, right, and show it.
Okay.
That may be a little bit.
I can look for the deck while you're doing that.
Yeah. So
why you guys doing that?
What's that?
I have why you guys doing that? I think I have a quick question for having with Petri, like about just now when you mentioned about that the limitation is our interface, right? So from your initial simulation. Ahmed, Petri, are you guys still there?
So typically in the system level performance simulation, we have two different areas that we are observing. One is the processing resources need, and the other one is the data traffic.
All right.
And on the data traffic, is there also a performance metric to that, right? In terms of bandwidth or latency.
So in the performance model that we are using, it is a real virtual platform that has AXI bus. But what we can analyze are other queues. What is the queue processing time? And this is one of the traces that we have. We are still working on some parameters on the data traffic analysis. So I was not able to show that how we can change the data size parameters there. But this is already part of our example.
Okay. Yeah. So we can if there is an interface between two blocks, there is a way to modulate how much time actually it takes for the data to go to that interface. Not necessarily at the axis level, but in terms of that actual link, right? The data flowing from one point to the other is not going to happen instantaneous. And whether that's modeling in terms of data flow or two different components, kind of like subcomponents of the SoC, that would be the actual interfaces. Okay, that turned out into a very long question because I digressed into explanations. But my question is, there is some way to estimate the time impact of one type of interface versus a different type of interface?
So we have methodology. The example that I showed to you, it was all inside one CPU cluster.
Yeah.
But if we make a system that has multiple SoCs or even multiple ECUs, then we have, at the moment, we have Ethernet and we have CAN bus. And we can principally build any type of interconnect to analyze the communication of different types of channels.
Okay.
All right. So David, why don't you just walk through
Yeah,
this,
so-
your slide here?
So for the OCP demo that we briefly started for the Global Summit, and we would like to expand on for the Chiplet Summit and for the next year's Global Summit, is basically what we just briefly built is a system which includes 4 CPUs, and each CPU gets an HBM memory. Inside this each CPU, we have I forget how many, probably 16 RISC-V cores.
16, yeah.
Yeah, and the connectivity shown here is basically each CPU is connected to one HBM, and then CPU to CPU we have BOW interface, right? That has a given width and a given speed, right? Whatever whatever the standard says. So what we I think would like to do is being able to estimate the performance of this system, right? There's always a question when there is SoCs or multiple SoCs, which we call chiplets in this case, right? Because we put them all on single substrate. So all these different chiplets with a given performance, or in some cases, let me backtrack a little bit. So the chiplets are going to be two kinds. One is ready-to-go chiplets, and the second one is a custom chiplet that we are building, right? So in this case, we are looking at that the CPUs are fully custom chiplets. So what we would like to estimate for this kind of a custom chiplet is, okay, we have the CPU cores, but what is going to be the actual performance of the system, right? Including the chiplet to chiplet communication overhead.
Yeah, or the other way we could view this is think of it as, the way I was looking at it is, Petro, you could define some arbitrary system level application that we're building, and it's going to require a certain amount of CPU processing. And the idea is we would have these kind of predefined, we have a 16 core RISC, we could even build another chiplet that's 64, and then you can explore, come up with a recommendation for that microarchitecture based on maybe 2 different of these chiplets that are predefined, or even, just have a conceptual model, like before we even build a chiplet. You want to do this analysis kind of at a very high level before you start implementing. So that's what I was thinking about. And then, looking at the memory bandwidth and the data bandwidth, analyzing those two. So is that something that you think we can kind of put that system level tool on top of this demo, and actually maybe create 2 different design scenarios? Then we can look at, maybe you have 2 that are viable, and then we can then pull it in and look at, the thermal implications, or for each of those, and say, all right, these are both good from your perspective, but from a practical perspective, we want to look at different things.
I'm afraid this will not be doable with a
No.
short notice, because we need to create models for
Well,
these communication channels.
Well, the notice doesn't, you know, how do you define short? Because I think, you know, we're looking at probably 6 or 7 months to build this demo.
Okay. Ahmed, what do you think? We need R&D help to make that.
Yeah, it just a model, Petri. So
it is just a model, but
yeah,
somebody must write it.
yeah. So Tony, as you know, when we build model, we need justification why we need to build it, and if we can,
Sure. Yep.
if we, and I know you are developing the team internally, and it seems to do that. So
Yep.
if we can justify it and put the reason,
Okay.
then absolutely doable.
Sure. Yeah. Okay. So I would just need rough order of magnitude. You know, how much of an effort, how long it's going to take, and but it sounds like conceptually this is something that we could do.
Yeah. No, this is exactly the things that the tool is designed to, and the reason why we show you very limited example here, because it's limited to very AutoSAR type application that we have a lot of model for it.
And the other thing we could do is we could have an ARM chiplet, and we can have a RISC-V chiplet, right? And we can look at those two and look at So I think that would be cool, because it sounds like you guys already support ARM, and I believe we can get access to some ARM IP and ARM libraries that we could actually physically build. So that would be interesting.
Yeah, and different level of communication and different interfaces and things like that. It's all configurable in a way. If we can build a generic interface, then we can configure it manually, or build it specifically to the spec you need, and then you have it as a library.
Yeah, and it would be nice maybe to compare BAO versus UCIe Express, right? So that's another variable that, you know, that if there's data throughput implications. So I think that would be a very powerful demo.
Yeah, if you see our interface now, how we configure it, just pull down menu, and we said, okay, is it Ethernet or CAN, and you can switch it on the fly and run two scenarios. So the same thing here will apply to your examples. Like pull down menu, you pick what type of interface you want, what type of RISC-V or ARM, and then you run an example.
Yep. Okay. Good. Yeah, we're running over, but this is very good. Thank you, Petri.
This would be very great example, because we are kind of missing real world examples that we can get the data that we can build the model.
I'm not sure I would call it real world, but you know, it's closer to the real world, and it gives us a path to get to the real world, where if we can get access to the actual IP and libraries, then we could actually make something that could be real. To make it real, you have to fab it. That's a little more expensive, but at least if we could build it, I think that would be very interesting. And the other thing is also in the chiplet world, you know, you have the variable in terms of what technology. Do you want to do this in a 16 nanometer or 5 nanometer? And I don't know how. I guess that would be predefined libraries, I guess, from one perspective, from your perspective, right? You're not gonna really, you're really not technology specific in terms of the implementation. So you would just be using, say, a 16 nanometer ARM core or a 5 nanometer, right?
Yes. So.
Okay, guys, we are kind of quite over the time.
Yep.
Thank you for the great presentation. This is very, very interesting, and I think definitely we can apply it on the test case that we've been working on. So, Tony, are you going to be here next week at CDX?
I will be in Japan next week, so
Okay.
the answer is no.
So eat lots of wasabi. There was
I
think
plan on it.
Yeah, research came out that improved memory. So, all right, guys.
All right.
Thank
Hey,
you, everyone.
thanks,
Thanks,
Ahmed.
Guy.
Thank you.
Everyone.
Bye.
Great
Next week.
presentation. Yeah. Bye.
Thanks.
Thank you.
Thanks.
Thanks.
Bye-bye.
Thank you. Bye bye.
Thanks. Bye.